Hey everyone, I am Ms. Hu, your physics teacher. In this video, we'll be going through momentum, specifically the principle of conservation of momentum. So what we'll be covering in this video lesson are momentum, the principle of conservation of momentum, as well as the types of collisions. So first things first, we must know what momentum is. Momentum is quite simply the product of mass and velocity. This is the equation for momentum, where you take mass multiplied with velocity. The definition of momentum is based on the equation. So momentum is one of the many physical quantities where the definitions are based on the formula of that physical quantity. That's why over here I've written the definition of momentum, which means that this line is the definition of momentum. So momentum is the product of mass and velocity. The units for momentum can be derived from the formula. If we know that momentum is mass times velocity, what we need to know is the units for mass and velocity. In this case, we're going to write the SI units. So the SI unit for mass is kilogram, while the SI unit for velocity is meters per second. So when we multiply this together, we would get the unit for momentum as kilogram meters per second. So this is the SI unit of momentum based on the formula. Now, another accepted unit of momentum is Newton second. So that's NS, capital N, small s. So you can either use kilogram meters per second, or you can use Newton second as the unit for momentum. In case you're wondering how on earth we got Newton second, this is explained in my other video of momentum, which involves impulse and impulsive force. So I won't touch on that. If you'd like to know more, go watch that video. So speaking of impulse and impulsive force, just to let you know, generally when it comes to momentum, the concept of momentum covers two topics. So one topic is on impulse and impulsive force, and the other topic is on principle of conservation of momentum. Now in this video, I'm not covering both topics because it can be quite a lot of information and I don't want to overwhelm you at this point. So I've split momentum into two videos. So this video will be focusing on the principle of conservation of momentum. So let's get to it. What is the principle of conservation of momentum? So the principle of conservation of momentum states that in an isolated system, the total momentum of two or more bodies is the same before and after a collision or an explosion, unless an external force is applied. That means that if you have a situation involving the collision or explosion of two or more bodies, the total momentum before and after are equal, unless an external force is applied. If there's no external force, then it's an isolated or a closed system. Now, if this doesn't make any sense, don't worry, I'll be explaining it more in the next few slides. So, to understand this, let's take a look at a general example of a collision. So, say in this diagram, the blue and green balls are going to collide. So, what we're looking on the left side here is before collision, this is during collision, and this is after collision. So, we have, in this case, two objects which will be colliding. So, I'm going to label these as objects 1 and 2. Now, the principle of conservation of momentum states that the total momentum before collision is equal to the total momentum after collision in an isolated system. So, which means that before collision, each object would be moving on its own. So, there are many ways in which this collision can happen. You could have object 2 stationary and object 1 moving and it collides. Or you could have a situation where both are moving and one collides with 2. Or they could be both moving in the opposite direction and it's a head-on collision. So after collision, also you could have both moving separately, or both moving in opposite directions, or one's not moving and the other is moving, or you could have both moving together. There are many situations in this, regardless of whichever that happens before and after. There's a collision here, it's an isolated system, total momentum is equal before and after. So, just for the sake of this example, let's say both objects were moving in the same direction initially. So I'm just going to draw an arrow. This is arbitrary. Remember, they could be moving opposite directions, doesn't matter. Because this is before the collision, both objects are moving with their respective initial velocities. So initial velocity is normally represented with the letter U. These could be different, so I'm going to label this as U1 and U2. Now, after the collision, they could be moving separately, they could be moving together, doesn't matter. I'm just going to draw the directions with arbitrary labels here. After collision, the objects will be moving with a final velocity. So the symbol normally used to represent final velocity is the letter V. And it is possible they're moving with different velocities, so I'm going to label this as V1 and V2. So U1 and U2 are the initial velocities of object 1 and 2 respectively, while V1 and V2 are the final velocities of object 1 and 2 respectively. Now, momentum is the product of mass and velocity. So each object could have their own values of mass, which I'll label here as M1 and M2 for objects 1 and 2 respectively. Before and after collision, the masses would be the same. There's no reason why the mass would change. So which means that after collision, they would still be M1 and M2. So momentum is mass times velocity. So for object 1, the initial momentum would be M1 U1. So M1 times U1. For object 2, the initial momentum would be M2 U2. For the momentum after collision, the final momentum of object 1 would be M1 V1, while the final momentum for the second object would be M2 V2. So what I've written here are the respective momentums for each object before and after collision, because momentum is mass times velocity. Now, based on the principle of conservation of momentum, the total momentum before collision is equal to the total momentum after collision. So total momentum in this case is summing up all the values of the momentum of that situation. So before collision, we're going to total the momentum. So we can put this as M1 U1 plus M2 U2. Same thing with final momentum. The total final momentum, we will take M1 V1 plus M2 V2. Total momentum before is equal to the total momentum after collision. So this formula is the derived formula based on the principle of conservation of momentum. So we would use this formula to solve collision or explosion questions where the momentum is conserved. Now at this level, we will only look at two objects, but just bear in mind that the principle of conservation of momentum could involve collisions with more than two objects. So you could have 3, 4, 5, 100 objects. In that kind of situation, the formula would just need to be tweaked to match the number of objects. So an easy way to remember this is generally the sum of mu is equal to the sum of mv. So this is the mathematical symbol of sigma, which represents total. Total mu is equal to total mv. So if you have more than two objects, then you have m1 u1 plus m2 u2 plus m3 u3 plus m4 u4 until how many objects you have. And then on the other side, same thing, it's equals to m1 v1 plus m2 v2 plus m3 v3 plus m4 v4 and so on and so forth. So if you have trouble remembering this formula, what you can do is just remember total mu equals total mv, and you open up based on the number of objects involved in that event. Now, before we go into the application of the principle of conservation of momentum, let's learn about different types of collisions. Generally, there are two types of collisions that you need to know about. One is an elastic collision, while the other is inelastic collision. For elastic collisions, true elastic collisions will conserve not only the momentum, but also the kinetic energy. So that means for true elastic collisions, both momentum and kinetic energy are conserved. However, for inelastic collisions, for true inelastic collisions, only momentum is conserved, while some kinetic energy is lost. So as you can see, the main difference between these two types of collisions is that for elastic collisions, the kinetic energy is conserved, while the inelastic collision, some of this kinetic energy would be lost. Now, let's look at the formula for the principle of conservation of momentum applied in different situations. So we're going to solve them for different events. So generally, after collision, the objects might move separately or the objects could move together. We're also going to look at the event of an explosion because remember that principle of conservation of momentum applies not only for collisions but for explosions as well. So when we talk about objects moving separately after collision, it doesn't matter how they first started. So remember earlier I mentioned you could have one stationary, one moving. You could have both moving the same direction, or you could have both head-on. The key thing here is that after collision, the objects are moving separately. For example, if you were playing billiard or snooker or pool, the cue ball would hit the colored ball and they are moving separately after collision. So in this case, there's actually no changes that need to be made to the formula because you would have the respective u1 and u2 representing the initial velocities of object 1 and 2 respectively, and same thing for v1 and v2, which represent the final velocities of objects 1 and 2 respectively. So of course, the masses for the objects are m1 and m2 respectively, and they don't change before and after collision. And as you can see, based on the principle of conservation of momentum, m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So just to show you the example of objects moving separately after collision, like I said, you have a cue ball hitting pool balls, and you can see how the balls move separately after collision. Now another very common and famous example of the principle of conservation of momentum in practice is Newton's cradle, because as you can see, when one of the balls is lifted and it collides with the others, one ball would be moving separately from the others. Provided the masses of all the balls are equal, you would see a perfect transference of momentum. So this is a perfect example of true elastic collisions. Now let's look at an example where the objects move together after collision. So again, it doesn't matter how the objects were moving before collision. Remember all the different examples I talked about. The key thing of this situation is that after collision, both objects are moving together. Now, the same formula can be applied, but just to show you how it could be modified for an easier way to solve the question in this case. So we again have u1 and u2 for the initial velocities respectively for objects 1 and 2. And for the final velocity though, you can still label it as v1 and v2. But the difference between this type of event and the earlier event is that v1 and v2 are equal because now they're moving together. So there is a common final velocity. So I'm going to write here v representing both v1 and v2. So both will be moving with the same velocity of v. Of course, each object will have their own respective masses of m1 and m2. If we take a look at the formula which we derived earlier, which was m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2, a slight modification could be made on this formula because now v1 and v2 are equal. So to represent the common velocity, we'll just use the symbol v. So we will get m1v plus m2v. And as you can see from this line, we can take v out as a common factor. And taking v out as the factor, we'll be left with m1 plus m2, which we'll put in a bracket here. So a simplified formula would be m1 u1 plus m2 u2 equals to bracket m1 plus m2 v. So you can think of this as, yes, both objects are moving with the same common velocity, that's why I've taken v out. And you can also think of it as the reason why we take m1 plus m2 is because now both of them are moving as one unit, so the masses have now combined to act as if they're one large object with the combined masses of m1 and m2. That's why we add them together. So this is a simplified formula you can use for this situation. So an example of a situation like this, possibly a car crash, because when cars collide with each other, the cars have a crumple zone that causes them to get dented in and they smash into each other, and you can see they kind of move together for a short while. So this is one example of objects moving together after collision. Now let's look at explosion. So explosion is a situation where both objects start out in a stationary position and an explosion occurs, forcing them to move in opposite directions. So let's say these objects are objects 1 and 2. They have their respective masses of m1 and m2. For their velocities, because this happens after the explosion, this is the final velocity, which I'll label as v1 and v2 for objects 1 and 2 respectively. Now, in the case of explosion, we can still apply the formula for the principle of conservation of momentum. But let's look at how to simplify that equation. So the equation is m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Now, remember I mentioned earlier that an explosion is when the initial velocities of the objects are 0, because they're both stationary. That means in this case, u1 is 0 and u2 is also 0. Now, anything times 0 will be equal to 0, which means that m1 u1 will be equal to 0. So in case you're wondering what I've just done here, this is just a mathematical way of simplifying our equation, because anything times 0 will be equal to 0. So if u1 is 0, m1 u1 is equal to 0. So we draw an arrow across this combination and put a 0 here to show this whole thing is equal to 0. You can only do this when the value is equal to 0. If it's another number that is non-zero, you cannot do this. All right? So this is just a mathematical way to simplify our equations to nullify or zerify that particular part. So we're going to do the same thing for m2 u2 because u2 is also 0. So m2 times 0 would be 0, which means that the entire left side of this equation is equal to 0. On the right side, we have m1 v1 plus m2 v2. Now, you can leave the equation as is, or if you want to simplify even further, we can bring one of this to the other side. So let's bring m1 v1 over to the left side. So when we bring this over to the left side, this becomes negative. So negative m1 v1 equals to positive m2 v2. So this is the simplified equation which we can use for explosions. Now the negative here is important because the negative here indicates that the velocity is in the opposite direction. That's why in an explosion, the objects will always move separately in opposite directions. They will not be traveling in the same direction. Based on this equation, this shows us that the magnitude of the momentum of object 1 is equal to the magnitude of the momentum of object 2. The only difference is that they're moving in opposite directions. So the momentums are equal because they will have to balance each other out to make them equal to 0. Because remember, total momentum before explosion is equal to the total momentum after explosion. That's why if it's 0, one will be negative, one will be positive. So an example of a situation which has an explosion would be the firing of a gun. So that's why every time you fire a gun, you have the gun recoiling or moving backwards. So this is true for any type of gun, whether it's a real rifle or a real handgun with a bullet, or even if you're just shooting Nerf bullets or paintball gun or paintball pellets. So here's to show some people do not expect the recoil of the gun to be so great, so that's why they're completely unprepared for the gun moving backwards, and that's why sometimes the gun might accidentally hit them and injure them in the face. So if you are going to be handling guns, please listen to your instructor and handle the guns very, very carefully. Now putting that all together in a summary sheet, So the principle of conservation can be applied in many different kinds of situations. So we have the object moving separately after collision. So for the situation where the objects move separately after collision, we do not have to change the formula for the principle of conservation of momentum. So you can just put m1u1 plus m2u2 equals m1v1 plus m2v2. For objects that move together after the collision, we know that they share the same final common velocity. So that's why we have m1u1 plus m2u2, and you combine both masses as if they're behaving like one big mass object, and v to represent the common velocity. For explosion, they would be moving separately after explosion, so you can have negative m1v1 equals to positive m2v2. By the way, for the explosion, even if negative was on the other side, like you have m1v1 equals negative m2v2, it still works. It doesn't matter whether the negative is on the left or right side, as long as you have the negative there to show they're moving in opposite directions. Now, do you need to memorize 3 formula for the principle of conservation of momentum? Well, if you want to, but if you feel like you don't want to memorize so many formula, but you can definitely remember the main formula of the total mu equals total mv, and you know how to derive it and apply them into different events, then you don't have to memorize so many formula. You just need to remember that the total mu is equal to the total mv, and then just derive it from there. Now, I'm not going to leave you here high and dry. I'm going to walk through with you some worked examples so that you will learn how to interpret the question and then substitute the values correctly into the formula. So the first example we're going to look at is this. Now, every time you want to solve a question involving the principle of conservation of momentum, you should always identify the objects that are involved in that situation. That means you got to identify objects 1 and 2. If there are more objects, then objects 3, 4, and so on and so forth. So at this level, we're just going to look only at 2 objects. So look for objects 1 and 2. So in a bowling game, Shelly throws a 5 kg bowling ball into the lane and it hits 1 pin. Both ball and pin move in the same direction after collision. So this is a linear momentum situation. That makes it easier for us to solve. If the ball was initially traveling at 8 meters per second and the mass of a bowling pin is 1 kilograms, calculate the velocity of the bowling pin if the ball travels 2 meters per second after collision. So the objects here are the bowling ball and the pin. So we'll take bowling ball as object 1 while we take the pin as object 2. So it's important that we identify which is object 1 and 2 because we have to make sure that our substitution for m1 and m2 are correct. If you get confused about the numbers, it is always a good idea to write a list at the side to help you stay organized about how you're going to substitute the numbers. So I'm going to write here on the side, m1 equals to 5 kilograms. Now the mass of the bowling pin as written here is 1 kilogram. So I'm going to write here m2 is 1 kilogram. Now the ball was initially traveling at 8 meters per second. So this is the initial velocity of the ball. So that's u1 as 8 meters per second. They want us to calculate the velocity of the bowling pin if the ball travels 2 meters per second after collision. So after collision, it's 2 meters per second. Which one is this? This is the ball, which is 1. So that's v1 equals 2 meters per second. Do we have u2? It doesn't say in the question. But if you know bowling, obviously the pin isn't moving. If the pin's moving when you throw the ball, that's not bowling, right? So that means u2 is 0 because the pin was stationary. Do we have v2? No, we don't, because we are supposed to be calculating this value because we're calculating the velocity of the bowling pin. So now that we have the list of information on the side, what we do next is we need to substitute the values into the equation. So this is a collision question, so obviously it's a principle of conservation of momentum application. And that's also pretty obvious because it's in this video. So we're going to write this out. m1u1 plus m2u2 equals m1v1 plus m2v2. Now in case you're wondering, how do we know when to use this and not one of the other simplified formula? So if you're in doubt, always write out this full equation first, and then you figure it out from there, whether the objects are moving together or separately after collision. In this case, it's quite clear they're traveling separately because they're asking you to calculate the velocity of the bowling pin if the ball travels 2 meters per second. They didn't tell us they're moving together. The question would normally tell you whether the objects are moving together or not. For now, let's just substitute the values in. So we will substitute the values in here based on our list. So we have 5 times 8 plus 1 times 0 equals to 5 times 2 plus 1, and we have an unknown v2. So this is 0, so I'm just going to scratch that out. And this leaves us with 5 times 8, which is 40. 5 times 2 is 10, plus 1 times v2. Solving this, you get v2 as 30 meters per second. Whether this value is logical or not, never mind, we've got the answer. Let's look at another example. So in a remote-controlled car race, Alfred's car of 1.5 kilograms and Jamie's car of 1.8 kilograms crash into each other during one of the laps and continue to travel together after collision. Calculate the final common velocity of the cars if Alfred and Jamie's cars were initially traveling at 3 and 2 meters per second respectively. So you can see that in this question, they tell us clearly that the cars travel together, and they even told us to calculate the final common velocity. So the question already tells us very clearly which type of collision this is. The objects are moving together after collision. If you want to write the list out of symbols with the values on the side, you can also do that. So let's take Alfred's car as object 1 and Jamie's car as object 2. M1 is 1.5 kilograms while M2 is 1.8 kilograms. Alfred's car was moving at 3 meters per second initially, while Jamie's car was moving at 2 meters per second initially. You are looking for the same final common velocity, which I'll label here as v. So if you already know that the cars are moving together, you can straight away write the equation that has been simplified for this kind of collision. So m1u1 plus m2u2 equals to, combining m1 and m2 together into one object, we'll put that in brackets, and the final velocity of v will be on the outside. So all we need to do now is just substitute 1.5 times 3 plus 1.8 times 2, and then inside this bracket is 1.5 plus 1.8 common velocity of v. So from here you would get 8.1 on the left side and 3.3 v on the right side, and this will give us v. Always make it a habit to write the subject on the left side. V equals to 2.45 meters per second. And that's how you solve this kind of question. Example 3. Two carts on a straight track collide head-on. The first cart was moving at 3.6 meters per second to the right, and the second was moving at 2.4 meters per second in the opposite direction. After the collision, the second car continues moving in its initial direction of motion at 0.24 meters per second. If the mass of the second car is 5.0 times that of the first, what is the final velocity of the first car? So if you're looking at this like, oh, this looks so complicated, don't worry, it's really not. All you need to do is just look for M1, M2, U1, U2, V1, V2. And then after that, you just need to substitute what you have inside the formula. So we've got two cards. Let's take the first card as object 1. So this is object 1. And the second card is, of course, object 2. So let's write out what we have. Do we have M1 and M2? Not in the first sentence, but they did tell us that the mass of the second car is 5 times that of the first. So if we don't have that, let's just leave M1 as M1. Second car is 5 times of M1. So I'm going to write here as 5M1. Don't worry if you're wondering, oh, how come there's no number here? You'll find that because of this relationship, eventually you'll cancel out the unknowns. Let's go into U1 and U2. Do we have the initial velocities? Yes, we do. So the first cart was moving at 3.6 meters per second to the right. So they've given us a direction here, and let's take to the right as positive. So we have U1 as 3.6 meters per second. Now the second was moving at 2.4 meters per second in the opposite direction. So you cannot just write U2 as 2.4 meters per second. In the opposite direction, remember that momentum involves mass times velocity. Velocity is a vector quantity, which means that there must be a negative applied in the number if it's moving in the opposite direction. So that's why U2 is negative 2.4 meters per second. After the collision, the second car continues moving in its initial direction of motion at 0.24 meters per second. So we have, let's write V1 and V2 here. The question is asking us for the final velocity of the first car. So we do not have V1. So I'm going to put question mark here just to indicate that's the unknown that we're looking for. The second car continues moving in its initial direction. So initial direction was negative, so we'll keep the negative here, but now its value of V2 is 0.24 meters per second. And now we substitute. So M1U1 plus M2U2 equals M1V1 plus M2V2. In case you were wondering, I'm reading this question and I'm not sure, are they moving together or not? Whenever in doubt, always write them out separately first. If they happen to be moving in the same direction, as you substitute the values in, later you can always convert the V1 and V2 into V. And in this case, very clearly, the two objects are moving separately. So now let's substitute. We don't have the value of M1, so we're going to leave that as M1. So U is 3.6. M2 is 5M1, so we're going to put here 5M1. U2 is negative 2.4. So M1 is unknown, so leave it as M1. V1 is also unknown, that's the one we're looking for. M2 is 5M1 and V2 is negative 0.24. So what we'll have here is 3.6 M1 minus 12 M1 M1V1 minus 1.2 M1. So as you can see, you have M1 in every single variable in this equation, which means you can actually cut M1. So if you're good at math, you can do that. But in case you can't see it and you're not sure whether you can cut it or not, you can always take M1 out as a factor. So we're going to simplify this first. 3.6 minus 12 gives us negative 8.4 M1. And over here, we're going to take M1 out as a factor. So you have M1 bracket V1 minus 1.2. Now you can see you can cut M1. So that's why, even though we don't have M1, we can solve the value because they've already given us the comparison between the two masses. So this leaves us with negative 8.4 equals to V1 minus 1.2. So solving this, bring V1 to the left side, and what you'll get is negative 7.2 meters per second, which means that the first cart will now be moving to the left, opposite to its own initial direction. That means moving in the same direction as the second cart. So remember that when you have a second object moving in the opposite direction, you must put the negative in the values. Example 4. A bullet fired from a gun travels at 300 meters per second. If the mass of the bullet is 5 grams and the mass of the gun is 2.5 kilograms, calculate the velocity of the recoil of the gun. So this is very clearly an explosion question. You can use the explosion formula immediately. We know that the explosion formula is negative M1V1 equals to positive M2V2. Taking the bullet as object 1 and the gun as object 2. So let's write the list of values out here. M1, M2. There's no U1 and U2. We don't need that because remember that for explosion, U1 and U2 are equal to 0 because both objects were stationary at the beginning. So we only need to find V1 and V2. So the bullet travels at 300 meters per second after being fired. if the bullet is object 1, that means V1 is 300 meters per second. The mass of the bullet, M1, is 5 grams, while the mass of the gun is 2.5 kilograms. The velocity of V2 is unknown. Now, before we substitute the values into this equation, take a closer look at the mass. They've given us the mass of the bullet in grams, while the mass of the gun in kilograms. When you want to substitute the values of the masses into the equation, we have to make sure that they have the same unit. So ideally, we should always convert it to SI units, which means that M1 is equal to 0.005 kilograms, where we take 5 divided by 1,000 to get the value in kilograms. I'm just going to draw a line here for clarity. And let's substitute the values now. So we have negative 0.005 times 300 equals to 2.5 times V2. We have negative 1.5 equals to 2.5 V2. We're going to put V2 on the left side because we always want to make the symbol that we're solving, because we always want to put the variable that we're solving for on the left side as the subject. And we would get V2 as negative 0.6 meters per second. And that's how we solve this question. And the negative here indicates that it's moving in the opposite direction to the other object. And now we've come to example 5, which is the final example in this video. Azizul, who has a mass of 68 kilograms, is standing on a stationary skateboard with a mass of 3.4 kilograms. As he jumps off the skateboard, he notices that the skateboard moves in the opposite direction. Calculate the velocity of the skateboard if Azizul had jumped off the skateboard at a velocity of 1.2 meters per second. So, in this case, if you look, there's no collision. It's about a boy who's standing on a skateboard and he jumps off. So, how does the principle of conservation of momentum apply in this case? This is an example of an explosion because Azizul, who's on a stationary skateboard, they're both stationary at the beginning. Then he jumps off. This is simulating the explosion process. And as he jumps off, the skateboard moves in the opposite direction. So yes, this is actually an example of explosion. Now, we know the explosion equation is negative m1v1 equals to m2v2. We can write down the values of m1 and m2 on the side here, so it helps us with a substitution. Again, u1 and u2 not necessary because they're equal to 0. So we only need to find v1 and v2. So we'll take Azizul as object 1. He has a mass of 68 kg, so m1 is 68 kg. The skateboard will be object 2, and that has a mass of 3.4 kg. So calculate the velocity of the skateboard. So this is the unknown. Skateboard is object 2, which means v2 is the one we're looking for. So v2 is unknown. Azizul jumps off at a velocity of 1.2. That means v1, which is Azizul's velocity, is 1.2 meters per second. So now let's substitute in. We get negative 68 times 1.2 equals to 3.4 times v2. On the left side, we have negative 81.6. On the right side is 3.4 v2, making v2 the subject. The value of v2 will be negative 24 meters per second. And that's how we solve example 5. And that is it for this video. So if you found this video to be educational and helpful, do click like and comment. Please help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, do check out my website at physicsrocks.com. Subscribe for more physics lessons from your physics teacher, Ms. Ho, and check out my YouTube channel for videos on other lessons which you might find very helpful. Happy studying!